Now we continue from where I left off in the previous video. In this video we'll be discussing the position time graph, xt graph as we call it, and the vt graph, the velocity time graph as we call it, and later we will be talking briefly about what we call uniform motion. Now this is the position versus time graph. On the vertical axis we are representing x, the position of a particle. On the horizontal axis we are representing time, and this red curve shows the position at various points of time for this particular motion. Now we have looked at an interval of time from 0 to t0. Now for this particular graph, for this particular motion, the average velocity during the entire interval from 0 to t0 is essentially the total displacement by total time, and the displacement is x2 minus x0. x1 minus x0, and the time interval has a duration t0. So x1 minus x0 divided by t0 gives me the average velocity during the motion. So the average velocity is x1 minus x0 by t0. Now x1 minus x0 by this length t0 should give me the slope of this straight line that I draw from the initial point to the final point on the graph. So if I join the initial point representing this motion with the final point representing the motion with a straight line, the slope of this straight line gives me the average velocity. Now if I'm interested in working out the instantaneous velocity at a given point of time, what I need to do is at that point of time I look at a very tiny interval of duration dt, and during that tiny interval of duration dt the displacement that we get is this change in x, that is dx. See, this was x, right? This height was x, or you can say the height of this point from here, this was x, and the change in x was this dx. The instantaneous velocity at this instant would have to be dx by dt, and dx by dt would be the slope of this curve at this particular point. So instantaneous velocity at a time t equals the slope of this xt graph at time t. So we have two interpretations, two geometrical interpretations for the xt graph. The slope of the straight line joining the initial and final points representing motion, the slope of that line is average velocity, and the slope at a given point is the velocity at that particular point. Now the other graph that we study very often is the vt graph, and I have drawn a random vt graph for some random motion. Now we'll be looking at getting a geometrical interpretation of this graph. Now the instantaneous velocity is given by dx by dt, and if I take dt onto the other side, what I get is dx equals v dt. Now with this equation, what I'm going to do is dx equals v dt, I will integrate both sides. Now when I integrate the left hand side dx, the limits will be x0 to x. x0 is the initial coordinate at 0 time, and x is the final coordinate at time t. So we are integrating on both sides of the equation. On the left hand side, the variable of integration is x, so the limits are in terms of initial and final values of x. On the right hand side, we are integrating with respect to t, and so the limits are for t starting with 0 up to time t. Now when you integrate dx, now when you integrate dy you get y, so when you integrate dx you get x. Also you might quite easily recall that dx would be x to the power 0 times dx, and when you integrate you should end up with x to the power 1 by 1. So when you integrate dx, you get x, and when you integrate v dt from 0 to t, you get area under the vt graph in the interval from time 0 to t. You will easily recall here the area interpretation of the integration concept. This integral will be the area under the vt graph in the time interval starting 0 all the way up to t. Now when you integrate dx from x0 to x, what you end up with here is x to the power 1 by 1, and the limits are x0 to x. And when you substitute these limits in this function here, you get this x to the power 1 minus x0, and that's what you end up with on the left hand side of the equation, x minus x0. On the right hand side you have the integral of v dt from 0 to t. Now what you will notice is this integral of v dt from 0 to t equals x minus x0, and the integral equals the area under the vt graph. So area under the vt graph in a given time interval equals x minus x0, and x minus x0 is the displacement during that same interval. So the area under this vt graph, if I shade this area, this shaded area under the vt graph gives us the displacement during this entire interval from 0 to t. Now once we are clear with these geometrical interpretations, let's very briefly discuss a very interesting introductory concept in motion, and that is uniform motion. Now what is this uniform motion? Now in certain books, the not so great books, they say that uniform motion is a motion in which displacements of an object in equal intervals of time remain equal irrespective of the size of the interval. Now that is kind of Greek, complicated way of expressing what's a very simple concept. Essentially uniform motion is motion with a constant velocity, and if velocity is constant, then in equal intervals of time displacements will be equal. So the simpler way of expressing uniform motion is calling it motion with a uniform or a constant velocity. And when motion has a constant velocity, the slope of the xt graph will be a constant slope. Now if the slope is constant, the graph will have to be a straight line. It's only a straight line which has a constant slope. So in case of uniform motion, the xt graph will be a straight line. Now in this case, you notice the slope is positive, which indicates that the velocity is also positive. In case the velocity is negative, you will end up with a downward sloping graph having a negative slope. Similarly, for the same uniform motion, the vt graph, as I have drawn here, this vt graph, this will look like this over here. Velocity time graph for uniform motion. Well, since we have been told that in this motion velocity is constant, the vt graph is a horizontal line. Now a horizontal line means that at any point of time the magnitude of velocity remains the same. So for all values of t we have the same v, and this represents therefore vt graph for uniform motion. Now if you were to confirm this concept of area under VT graph as being displacement, it's very easy to confirm over here. When velocity is constant, displacement would be simply velocity into time. That's something you learned in class 9. Now this velocity into this time here obviously gives you the area of this rectangle, and that we already know is displacement. So area under the VT graph in a given time interval equals the displacement during that interval. Of course, this case represented positive velocity because velocity is above this time axis. In case the velocity is negative, this line would extend downward here, and v would be negative, so the graph would be below the time axis, of course still remaining horizontal. So that's the description of what we call uniform motion. A few simple examples based on the ideas we have covered so far. In the first example, we consider an object moving along this x-axis. It travels with a constant velocity v1 for some time, let's say t, and then stops and reverses direction and moves with speed v2 for the remaining half of the time. So for half the time the velocity is v1, for the remaining half of the time velocity is minus v2. We are interested in calculating the average speed and average velocity during this motion. Now let's say that half of the time from point A to point B, that half time was t, and so the time from B up to C, this was also t. Now to start with, we calculate average speed. Now to calculate average speed, we need to calculate the total distance, and this initial distance was of course speed v into time. This was the magnitude of this distance, and then from B to C the distance was mod of this velocity v2 minus v2 into time. This is already positive, so no need to take mod, and divide this total distance by the total time, which is 2t, and gives us average velocity. T cancels, and we end up with v1 plus v2 by 2. Now since this motion involves a direction change, we expect the average velocity to be different, and the calculation will not disappoint us. Let's have a look. Average velocity during this motion. Now the displacement is from this point A to this point C. Now you can actually add up both the displacements. First one is v1t and the second one is minus v2t, which gives us the length of this vector from A to C, and divide this by 2t, and we end up with v1 minus v2 by 2. That's the average velocity during this particular motion. Let's take another example, and this time we are told that an object is moving along this straight line and it travels half of the distance in the journey, let's say s, with a constant speed v1, and then it travels the next half of the distance, which is again say s, with a speed v2, and we are interested in calculating the average speed and average velocity during the journey. Now in this journey there is no change in motion direction, so average speed as well as average velocity will be equal. So let's calculate average velocity, and we will automatically know average speed. Now this average velocity will be total displacement. Total displacement here is 2s divided by the total time. Now during this first distance s, the time would be distance by the constant velocity here, plus the time from here to here will be the displacement again, s, divided by the constant velocity v2. S cancels out everywhere, and we get average velocity equals 2v1 plus v2, 2v1 into v2 by v1 plus v2. Another interesting problem that I would like to discuss on these ideas is, let's consider that this is a railway track, and on this railway track there are two trains, T1 and T2, which are approaching each other. They're on the same horizontal railway track, these two trains, and they're approaching each other, traveling with 30 kilometers per hour each. Constant velocities, 30 kilometers per hour each in magnitude, opposite in direction. Now initially the distance between these trains is 60 kilometer. Now at this instant, when we have started looking at this motion, a bird on this train takes off towards the second train, moving all the time with a constant speed of 60 kilometer per hour. Now the bird goes all the way here, and somewhere over here it collides with train T2, and on colliding with T2 it reverses direction and comes back. Somewhere here it collides with T1, which has now reached here. It collides with T1, reverses direction, goes towards T2, and then comes back, and so on and so forth. Now this bird just keeps shuttling between the trains till they eventually collide. Now since the trains are going to collide, the last few journeys will be extremely short, nearly zero kind of displacement. And when the displacements are kind of nearly zero, they take nearly zero time. And something that takes nearly zero time will happen an infinite number of times, essentially, and therefore the bird is actually making an infinite number of trips. What we have to calculate here is the total distance traveled by the bird in those infinite trips. Now this sounds like a really challenging problem, but it really isn't, because if we observe what's happening here, since the trains are traveling with equal velocities, they will collide right in the middle here. Since they collide right in the middle, each train travels 30 kilometers before colliding. Now when they travel 30 kilometers with a speed of 30 kilometers per hour, they each take 1 hour. So the collision happens after exactly 1 hour, and hence the bird was flying for 1 hour with a constant speed of 60 kilometers per hour. Now if you travel with a constant speed of 60 kilometers per hour for 1 hour, then the total distance traveled will be 60 kilometers. So that's essentially a very, very simple problem, a very basic example on straight line motion. Now we will be taking up further discussions on straight line motion very soon. In our next video we will be arriving at the concept of acceleration, and we'll be discussing about accelerated straight line motion. So far we have discussed uniform straight line motion. In the upcoming videos we discuss accelerated straight line motion as well. Also, before we actually move on to accelerated straight line motion, we will also be introducing the concept of what is called relative motion. So that will be the topic of our next video, relative motion, followed by the discussion on acceleration.